Okay, thank you. I'm really pleased to be joining you all, and this is a novelty. Of course, we're all adjusting in so many ways, and well, I look forward to being there in person in due course when we can do that. But in the meantime, let's get started. So before I even give you an outline of what I'm going to do, I'm going to sort of reveal my agenda a little bit. So physics is fundamentally quantum, and we have very specific and quite successful proposals for the quantum state of primordial perturbations. On the other hand, large physical systems do a fantastic job of hiding their quantum nature, which is, and if the universe isn't a large physical system, I don't know what is. So we've got that going on. And in fact, large systems do such a good job of hiding their quantum nature that we've been doing physics for many thousands of years and only discovered quantum in the last 100. And if we were together, maybe over beers, we could debate when to start the clock on these thousands of years, but that'll have to wait. So I'll just put that out there. So the big agenda is, given that we think we know we might well know the quantum state of the primordial perturbations, what are the prospects for identifying interesting quantum effects in the cosmos? And in particular, you know, the cosmos is a large physical system, so how does all that work out? So what I'm going to do mainly in this talk is review the tricks that large physical systems use to hide their quantum nature. And really the agenda is to invite you to develop insights about new quantum effects to look for in the observations we make of the universe. Certainly the universe works hard to hide its quantum nature, but we're also not very good at seeking it out, because we actually are so used to living classically, and of course as physicists we try really hard to go beyond that, but I don't think it's easy, and I'll have some examples at the end. So you might say, well, these ideas in cosmology have been around for decades. How do we, is there anything left to explore? And I'll give you some examples at the end of new ideas that just came out in this calendar year. And so there are new things to do, and we should, I want to set an invitation that each person at this meeting might be curious to, might end up discovering yet another opportunity to investigate such quantum effects. So it's really to equip each of you on your own path of discovery for this. And so the talk is actually much more about it's much more conceptual than technical. And it's a talk, so Jerome Martin and I have been kind of coordinating our two talks at this conference, and he will offer some technical things that are very nicely interwoven and interconnected with the topics I'm presenting here. So that'll make a good package. And of course, there's lots of interconnection with other talks at this workshop as well. So a couple of things of what this talk is not about. So this talk is not about the wave function of the whole universe. Specifically, we've separated out the perturbations rather than the background metric. So we're thinking about the background metric completely classically, and that's a convenient choice. The question of the background metric, we think we know what it is for the universe. The question about how it came about and what ensemble it might be drawn from, and are there quantum ideas that inform us about that, to me, those connect with topics that are extremely interesting, and I do like thinking about them a lot, but they're also very poorly understood. They're connected with the very origins of the universe, perhaps with the start of inflation, with the arrow of time and tuning problems. I love thinking about these questions. I can't resist just slipping in a comment that I think cosmic inflation is both under and overrated as a solution to the tuning problems. And I just leave that as a, I guess that means I think there's more, maybe we can improve the quality of our exploration of that question. This would be another way to say that. But by contrast, we have a good idea of what the classical background metric should be for this universe we live in, and very concrete proposals for the quantum state of perturbations. So, that's, for this talk, that's what I'm focusing on. This talk is also not about quantum measurement. I'm personally someone who is completely satisfied with ideas about quantum measurement that involve looking at the measurer and the measuree, both in the Hilbert space and how they interact with one another. This sometimes goes under the names of many worlds or the Everett approach to quantum mechanics. It's certainly the case that not everyone is satisfied in this way that I am. And some people even feel that major elements are missing from our theory, that this is, that quantum physics is far from a complete theory. And if you're in that category, and so in fact, some people are who feel this is such a problem that they don't even think you can really do cosmology because there's nothing outside the universe to do the quantum measurement. And in fact, such people often have trouble with quantum computation as well. And so if you're in that group, you might feel, well, I'm saying I'm not going to talk about this stuff. If you're in this group, you might be scandalized to think that I'm talking about the quantum to classical transition without talking about this stuff. And I'll just say that this is a reflection of the complicated relationship the physics community has with quantum theory. But I'm just going to acknowledge what I'm doing about all of this, how I'm doing this talk. So here's my outline. I'm going to introduce some key elements of quantum physics that are going to be essential to understand the emergence of classical from quantum. Then I'm going to talk about a little bit about how they operate in the actual universe, and then give some examples of recent results and some conclusions. So here we go. Quantum coherence. So the state of a quantum system is given by a wave function, which you construct by assigning a quantum amplitude to each element of some basis that spans the Hilbert space. And if you have two states that are possible states for the system, a linear combination is also a possible state for the system in your theory. And you can, this sort of goes by the name of quantum coherence. And note that even in the first expression I wrote down, since this is also a linear combination of states, these basis states, the quantum coherence has already showed up on the first line here. The coherence of a quantum state only means something in relation to what measurement you're going to make. So if you have some wave function that's just a classical wave packet, and you only ever expect to measure the particle in the wave packet basis, some localized thing in position momentum, then the particle simply moves from here to there, and there's really no meaning to the notion of quantum coherence in that case. And that's despite the fact that you might have viewed this wave function. This wave function is technically the set of amplitudes that multiply the eigenstates of the position operator. And that's, if you look at it from the point of view of these eigenstates, it looks like a very quantum coherent statement. But if you're only going to ever measure wave packets and the thing starts in a wave packet, there's really not much quantum coherence has to say to you. And I like to call this the relativity of quantum coherence. Quantum coherence doesn't mean something in the absolute, it's about relative. You have this particular state and you make this particular measurement. Sometimes that looks, sometimes that invites you to talk about quantum coherence and sometimes it doesn't. And so for example, the classic double slit experiment makes us think about quantum coherence because you enter into this double slit diffraction pattern, but then make the measurement in a highly localized basis by creating a spot on the screen. So you, it's this contrast. So you have this diffraction pattern state and you make a localized measurement, and that's where you end up thinking about quantum coherence. Alternatively, if by some magic you were able to construct a device, a measurement apparatus, whose pointer states were actual double slit diffraction patterns that you pass the particle through the screen and you make the measurements just in this one state. The pointer says this diffraction pattern, and you might in that case not actually particularly think about quantum coherence. Okay, next topic is quantum entanglement. If you have a, let's say the world is made of the system times the environment, you're often tempted, certainly in your first quantum mechanics course, you say, well, let's consider a state that's a product state where each of the subsystems is in a pure quantum state. But the general case is more complicated. It's this general entangled form. And it's a very quantum phenomenon. There's different things people say about this. It's definitely not spooky action at a distance, but it's other things you can say. It's certainly a very interesting quantum phenomenon. And in general, then, if you just look at the subsystem S, you can describe it by a density matrix, which you get by tracing out of the environment of this world state. Expectation values of observables in S can be written this way in terms of the density matrix. And in particular, you can write that in terms of the eigenvalues and eigenstates of this density matrix. And in that sense, this expectation value looks like a classical mixture in the sense that you're weighting each of these terms by what is essentially a classical probability, and there's no cross term. So each of these terms just has I on both sides. So this is something that's people tend to think of as a classical mixture. And in that sense, it's actually interesting. I've just said this is a very quantum phenomenon. Next thing I know, I'm talking about a classical mixture, and that's just, both of these things are true. As with the topic of coherence, the degree things look quantum depends on what questions you ask. So let's talk a little bit more about quantum entanglement. Interactions can create entanglement. So if we start with a total wave function that's made out of a state for the ball and a state for the photon, and here we're putting the ball in a Schrodinger cat state where it could either be here or here, and we're in this pure state before the collision, and then the collision takes place, and afterwards we would generally get into an entangled state. And let me try to illustrate that here, where the photon was incoming, and if the ball is here, it bounces off and goes off like that, whereas if the ball is there, the photon keeps going. And so there's now two different possible states for the photon, depending on where the ball was, and that's what creates entanglement. So I'm going to flip back and forth a little bit. So the entangled state is represented by these two cartoons taken together as we go between the two states of the in the two-term expansion. So in the example of the photon striking the ball, the Schrodinger cat initial state evolves into a classical mixture of localized packets. So what was originally a coherent superposition of these two wave packets becomes a classical mixture of the two wave packets. And this is actually the locality of the interactions, the locality of the photon state are important ingredients to make that work. And just to emphasize that, you could imagine perhaps sending in a coherent plane wave and getting a special pattern out which you could measure, and so there's different ways this can work, and different ways this would be like measuring it in a different basis, as I was saying earlier, and the Schrodinger cat nature of the initial state might be more exposed quantum mechanically in this kind of setup. Next, I want to talk about quantum Darwinism, and that's a term coined by Wojciech Zurek, and it's the sort of starting. So the way I'm going to tell it, the starting point is that the actual macroscopic world is awash with localized photons and air in these wave packets. So we don't just send one little photon in, they're all over the place. There's no waiting around to do the experiment. This is how, in the macroscopic world we live in, this is what nature is like. If you try to introduce a Schrodinger cat state, the environment will get there first. It's not going to wait for you to do some precious little experiment and send in the photon just the right way. The Schrodinger cat state won't get a chance, and these collisions will just happen immediately, and the kind of entanglement we discussed a few slides ago will just take place on its own without someone shooting in a particular photon. And so in the real macroscopic world, this is simply unavoidable. You could try to say, well, let's put the ball in the dark room, but you know there's going to be black body radiation from the walls of the lab and so on. There really is, in practice, no way of avoiding this in everyday experiences. Of course, if you're a hotshot experimentalist, that's your job to change this kind of picture. But this is about the everyday physics. And then another key point is that, how do we observe the ball? Well, we don't go in and build an apparatus and measure it. We just intercept one of these photons with our eye. And so the question of a measurement, or the question of the environment decohering other states, it's all the same thing. It's you're just sort of participating. You're sampling a small part of the environment when you observe the ball in our everyday patterns. And so in this sort of setting, the relativity of coherence is not a meaningful feature, because the environment makes all the choices. You don't get to choose what basis you're measuring the ball. The environment chooses it, and you just tag along, check out the environment, pick up a photon here or there. And so this whole idea that there's many different bases and you could pose questions different ways gets washed away by the presence of a relentless set of interactions with the environment that just keeps things under control. So there's the question of which states are prepared and which states you make the measurement in is all out of your control. There's only one basis that survives the action of the environment, and survival is sort of a word why you see Darwinism there, that there's really only the survival of the fittest in terms of quantum states of matter. So, and this is one of the reasons why we've been doing physics for thousands of years and only discovered quantum mechanics 100 years ago, because this is one of the ways large physical systems protect you from noticing their quantum nature. So moving on, there's another feature, which is that the wave function on its own, now let's forget about the environment. The wave function on its own can look like a classically evolving distribution. So I already actually touched on that a few slides ago. I kind of grabbed a screenshot from an earlier slide when I said, if you just measure wave packets, and a wave particle in a wave packet just moves from here to there, and there's nothing interesting about quantum coherence, you could say. But there's actually a more general, a generalization of this that is related to these conditions, which are often interrelated. They're not necessarily separate things. You can look at a system in a WKB limit. You can, in very general terms, if the Hamiltonian for the system is quadratic, this is true. And the Wigner function, if the Wigner function is positive everywhere, and you can, Jerome's talk is going to talk a little bit about what the Wigner function is, and how it's basically an alternative way of describing all the information that's in the wave function that looks a little bit more like a classical, that can look like a classical probability distribution if it's positive. And so under all these conditions, the information in the wave function can be modeled as a distribution in classical phase space, where each point in the phase space is just evolving according to classical equations. So in that situation, it looks classical. I mean, it's maybe you're solving the Schrodinger equation underneath it all, but it actually looks classical for practical purposes. as long as you agree to only ever measure the system in classical wave packets. So there's still, under these conditions, we've not introduced decoherence on this slide, and we're just talking about the evolution of an isolated system. Even an isolated system without decoherence can have a classical kind of behavior of the sort I sketch here. But unless you have decoherence, there's the potential to observe quantum coherence if you choose a different basis in which to make your measurements. And of course, quantum Darwinism comes into play, because under conditions where there is an environment that's choosing a particular basis for you, then there's nothing about agreeing to anything. You just blunder into the environment and you get what you get. So if you do have an environment, then there might be no ambiguity about making a measurement. If you don't, there could be well, there could be some coherence otherwise. So let's just putting some of these ideas together. Let's consider a macroscopic Schrodinger cat pendulum. So here's a pendulum. It's supposed to look like it's in a Schrodinger cat state, some linear combination of over here and over there. And let's imagine a totally empty room. So now I'm going to beg off the black body radiation and everything. Let's make it totally isolated. So this pendulum can be fully described, especially since it's quadratic. If we neglect the large angle corrections, it'll be quadratic. You can describe this in classical terms, classical phase space for all eternity, if you want. And the classical tools will do fine. And again, as long as you agree to measure this in wave packets, the classical ensemble picture will do fine. But then if you turn on the light, now you say, oh, let's have a look at this pendulum. Once you turn on the light, quantum Darwinism kicks in, and you lose the quantum coherence due to interactions with the environment. So then the decoherence process chooses the measurement basis for you, as I've said before. So now I want to shift to the actual universe, and I want to discuss the roles of these things in the actual universe. So most current theories of cosmology, yeah.
So this last point you are making is essentially that
Yes.
a purely a classical system could as well be described by a wave function. Is that the bottom line?
Well, I'm not quite saying that, because I could formally construct a classical system that, if I quantized it, would exhibit quantum effects, would not look like an ensemble of classical classical objects. But when I look at a quantum system that has some of these properties, then I can think of it as an ensemble of classical particles moving around in the phase space according to the classical equations, and there's there's conceptually that's a fine way to describe it.
Was the pendulum only two of the extremes?
I'm sorry, I'm sorry.
Was the pendulum meant to be in only one of the two extreme positions, or is it swinging as we are usually?
Oh, it's meant to be. So this cartoon is meant to represent a coherent superposition of these two.
The two extreme points.
Okay.
Okay.
Yeah.
Thanks.
So it's meant. So really, if I'd been overboard with my cartoon drawing, I would have had it swinging and everything. So you're supposed to think of this as time goes on. Each of these states swings back and forth according to the harmonic oscillator equations, and I can keep track of that using, because these are quadratic equations, I can keep track of that using classical. Think of it as a classical ensemble, just as well. Okay, so the next thought then is to think about the actual universe, and so most current theories of cosmology create the state of cosmological perturbations by taking the quantum field theory vacuum state and expanding it and amplifying it to all observable cosmological scales. That's a pretty dramatic statement. And by the way, this, as far as I'm not an expert on cyclic models, but I believe this is actually through a sort of circuitous path what happens in cyclic models as well. Someone might correct me if I've got this wrong, but anyway, I think that's true. The QFT vacuum is one of the most quantum states there is, just off the cuff. It's definitely not made out, it's definitely not localized wave packets. It's in fact, it's, you know, one of the special features of quantum field theory is that you have this quantum state. And however, the evolution, as it turns out, the evolution of the quantum state that you get in the cosmos, that you get on the large scales, is actually well described by a classical distribution. And this is partly, you can make the case basically that the evolution is essentially quadratic. Furthermore, even deviating from that, the cosmological evolution is connected with squeezing. This is something I believe has already been mentioned at this meeting, and that enhances the classicality. Again, as long as you agree to which basis you're going to measure it. Jerome Martin is going to talk about the squeezing. Here's a slide I grabbed from a draft of his talk that I saw earlier. So you're going to see this when you go to Jerome's talk. And then here's a paper from an ancient paper I wrote almost 30 years ago about the squeezing effect, where we really carefully analyze. We show how the squeezing that happens in quantum perturbations in the universe enhances the classicality from a certain point of view, as long as you agree which basis you're going to measure. And I've underlined here, the squeezing is actually even a classical, the notion of squeezing can happen in classical physics as well. And it's the same little squeezed shape that you're seeing in Jerome's slide, much more sophisticated slide, in this old paper of ours from long ago. And also, the squeezing comes about from having a growing and decaying solution, which I know David once mentioned in his beautiful talk at the start of this meeting. And so, okay, so one thing is that there's this quantum, the quantum state, once it's amplified to large scales in the cosmos, is actually behaving like an ensemble of quantum, like a distribution of quantum states evolving, a distribution of classical phase space evolving classically. But then also, there's tons of local interactions that will cause decoherence. So there's particles produced during reheating. If you're thinking about inflation, there's this cosmic microwave background, there's cosmic dust, there's all kinds of things around in the universe, there's starlight. And so these photons, if something's in one potential well or another potential well, get entangled, the positions get entangled with photons that fly across the universe. And it actually only takes one photon to create entanglement and create the kind of, to turn a coherent superposition into a classical mixture. And so that's, and so there's actually a lot of parallels. So I did this toy model, not by complete accident, to be parallel with the universe. So in the early universe, you have this quantum state, but it's evolving in this very classical way. And then eventually, there's all kinds of decohering effects that seem to pin down, that seem to destroy the quantum coherence, whether that's the light in the room or all the particles flying around and interacting in the cosmos. And so, so there's a lot of parallels. And one of the questions that, one of the conversations I've had many times over my career is, when is the first act of decoherence in the cosmos? And the thing is, it's not so clear it matters, because the classical evolution is evolving classically anyway. So certainly by now there's tons of decoherence. Do you really care when the first act of decoherence was? I'm not sure I do. So I've kind of wound up thinking about it that way. And actually, one other thing to add to this little series of slides is that the observations are made by just sampling a very small part of the environment, just like we said in this little thought experiment here. And of course, in the cosmos, that's all we're doing, is we're capturing a few photons or maybe gravity waves flying across the universe. So just, I'm moving along here. Okay, if I take a few more minutes? Urjit, you were muted, but you didn't
Yeah, yeah, I think about 5 to 7 minutes, certainly.
Okay, great. Okay, great. So I think I'll be fine with that.
We started a little late as well. So.
Okay, okay, good. So now let's just think a little bit more about the actual universe. So in popular theories, such as inflation, perturbations are made from an exotic quantum state, the quantum field theory vacuum. You would think this gives us opportunities to reveal interesting quantum phenomena in the early universe. Wow, the quantum, so in a theory like inflation, you're taking the quantum field theory vacuum, this exotic quantum phenomena, and just plastering it across the entire observable universe. And you'd think this would give opportunities to reveal interesting quantum phenomena as you observe the universe. However, the classically equivalent early evolution plus the huge array of subsequent decoherence processes seems to be working against you. So there's this tension. And so I want to now move to some examples and just talk a little bit about what it's like to further explore these questions. So, and this, I'm not going to get into each of these in detail, but the last point I want to talk about at greater length. So here's a paper by Juan Maldacena from 5 years ago, and he says, well, I want to, so he's basically taking this point of view that surely we can find some exotic quantum phenomena if we're putting the field theory vacuum across the universe. But what he realizes he has to do is whip together an extremely exotic inflation model. And I can't remember, I can't give you a soundbite about it because I've forgotten. My takeaway from this paper was it proves how hard it is. If Juan actually was trying to make some exotic quantum phenomena and had to invent this extremely concordant inflation model to try to make it work. So I would encourage you, so if you're trying to think, well, what could I do? Maybe discover something new. Maybe this is good reading just to see how desperate he was to get some interesting effect. There's this workshop at IPMU last year that some of us here were part of, and there's a lot of nice talks. A lot of people were a lot of very open discussion and nice talks about quantum effects in the early universe. I definitely recommend Jerome's talk at this conference. Oh, here, and also he had a much longer talk last year at IPMU that I liked a lot. There's this recent paper by Sugumi Kano and collaborators, and then I want to tell a little story related to this last point because it kind of illustrates the nature. It's not a terribly flattering story to me, but it illustrates sort of how these things work, how we can lose, we can miss things because we're not thinking right, because we can miss opportunities that way. So this is a slide from Sugumi Kano's IPMU talk at the workshop last year, and she was saying, oh, look, in quantum optics, there's this whole way of looking at the distribution of photon counts and the width of the distribution, and determining based on basically the width versus the mean of this distribution. They have a whole formalism that says certain properties. If this distribution has certain properties, you know it has to be quantum. It can't possibly be classical phenomenon. And I'm just going to say, I'm not going to get into explaining that, but just say this is a well-established thing you can read about in textbooks and so on from quantum optics. And so afterwards, so I was a little bit confused by her talk, but afterwards, Sugumi got in touch some months later and said, I want to apply this test to primordial gravitons. So we could, so here I've done some calculations and I've shown they're in the kind of quantum states that would trigger this test. And that surely will let us, do some really awesome test of the quantum physics of gravitons. So this is primordial gravitons from inflation. And so, but I came back and said, but how do you, so this is something in the lab, it has to do with individual photon counts. How do you count individual gravitons? And I really tried to think about it, and I asked some of my colleagues who are very involved in gravity wave detections, and no one thinks you can detect individual gravitons. And I have to admit, my thinking was influenced by this old paper of mine from 30 years ago. We were looking at this whole question of squeeze states, and even then we were thinking, you know, they're thought of as very quantum in quantum optics, but they're actually very classical from the cosmology point of view, because of the question of which bases you eventually were going to measure. And since no one measures individual gravitons, surely you're not going to get anything from the cosmology. So I was really pushing back. And then, interestingly, another paper came out which kind of ran with that idea and said, well, you don't have to measure individual gravitons. You can actually just look for noise in the gravity wave detectors, and this noise would be a reflection of the, you know, in some sense, a reflection of the individual gravitons. And so, in fact, they argue that this effect might even be observable in future gravity wave detectors. And so, and they really make a wonderful case of that. And so I feel a little bad, but rather, you know, I instead of sort of pushing back and saying, no, I don't think this is going to work, I wish I'd been more encouraging to Sugumi and been a little more clever thinking about it, like these authors were. But I'm really offering this as a lesson that we stumble. We really, even though we're physicists and we love quantum physics, we're used to thinking classically, and there may be other opportunities out there if we're careful, because we do have all this quantum physics we're putting into our theories of the primordial perturbations. So in terms of conclusions, just repeating, the popular theories of cosmic perturbations are made from an exotic quantum state. On one hand, this seems like an opportunity to see interesting quantum phenomena. However, there is a lot of the usual tricks that large systems play to hide their quantum nature that seem to be operating in powerful ways in the universe. But there's new ideas still coming out, and so I hope you feel provoked and stimulated to pursue some of these questions yourself. So I think that's a good stopping place for me, and our chair can decide how much we'll just wait later for questions, or I'll definitely be here at the official question period.
Okay,
so.
Great. So thanks a lot, Andy, for a very thought-provoking talk. I'm just scanning the chat to see, does Ashley want to ask his question now, or can it wait? I think, can you use measure of entanglement? So I think these are questions that probably can wait for the longer discussion. If you don't mind, Andy, you'll
either way, yeah. I defer to your judgment on that.
You can look at the chat as well, I think. But
okay, yeah. Once I
sure.
Sort of, yeah, I'm happy to do that as well.
Okay. Okay.
But well, I'm happy to continue. I'll stop my screen share, and I'll be around for the question period.
Okay. Thanks a lot, Andy.
Thank you.